So in this video, we'll be going over on solving differential equations by substitutions. So far we've actually been able to solve differential equations that are separable, as well as linear first order differential equations, as well as exact and non-exact differential equations. But it's not uncommon to find differential equations where it doesn't fit none of these methods that you're able to apply. So this is where we'll be learning on how to solve differential equations by substitution. So in order to use the method of substitutions, you first have to determine whether a differential equation is homogeneous or not. And that's nothing more than saying when you have some function of, let's call this constant lambda, lambda x and lambda y, you're able to actually factor out the lambda to the n power of that function. That means it's homogeneous. Now let's go ahead and let's do an example of this. So let's say we have this function with respect to x and y, which is equal to x squared plus y squared plus 2xy. Now, in this case, just to test it whether or not it's homogeneous, you just basically plug in lambda everywhere where you see a x variable as well as a y variable, and you get the lambda x squared plus lambda y squared plus 2 lambda x lambda y. Now, one thing you notice is you have lambda squared in each of these, and so you're actually able to factor out the lambda with to the second power here. So since in this case you were able to factor out the lambda, you have a homogeneous equation of second degree. So your power will be your degree of homogeneous that the differential equation is. And this is how you test. So if it is in fact homogeneous, then you can use this method of substitutions. So I would like to go over this example where it shows that it's not homogeneous. Now, if you plug in the lambda in each of for wherever the variable x is as well as the y, you see that right here you'll have lambda for this section, you have lambda squared. Then here you'll have also lambda squared. But here you have lambda for the x, and then you have the lambda squared for the y. So this one would be lambda cubed, and therefore you're not able to completely factor out the lambda here with respect to the function. You wouldn't be able to factor out the lambda completely since you have a cubed here and you have squared here. So therefore, it wouldn't be homogeneous in this case, and you would not be able to use the method of substitution. So now let's say you have a differential equation that is in fact homogeneous. Now what you're able to do afterwards is substitute either the y or the x variable for another variable that we have u. So you could either substitute y is equal to ux and plug it in your differential equation and solve. And then, or you're able to plug in for x equal to u times y. Now, once you're able to do this, you plug it in, and this in fact makes the differential equation separable and therefore easily solved by separation of variables. So let's go ahead and do an example. For this example, we have y squared plus y times x dx, take away x squared dy is equal to 0. Now, as you could tell, this is kind of very familiar to what we did in the exact differential equations. Now, let's just assume in this case it's we weren't able to solve for this differential equation. So one method that we do have is the method of substitutions. Now, just by observation, you could tell if you plugged in lambda wherever you had the x and the y variable, you will be able to factor out a lambda squared out of the entire function here, and therefore it will be a homogeneous of degree 2. So this in fact would work with the method of substitutions. Now let's go ahead and plug in y is equal to u of x and see what we get. So once we plug it in, it's equal to u squared x squared plus ux squared dx, take away x squared. Now remember, this is the derivative of y, so we'll be applying the product rule here. So you get u dx plus x du. Now let's go ahead and simplify this further. So after doing some simplification, moving some things around, after some algebra, you're actually, at the end of the day, you're left with dx over x is equal to du over u squared. Now from here, as you could already see, these are separable, so you integrate both sides and solve. So after integrating, you get -1 over u is equal to ln of x plus your arbitrary constant U is equal to 1 divided by the arbitrary constant take away ln of x. And remember, y is equal to u times x. So therefore, u is equal to y divided by x, which is equal to this. And then you just get y on one side of the equation. And this is your solution to the differential equation. So the method of substitution is nothing more is checking if the equation is indeed in fact homogeneous. If so, you can use this method. Either replace the y is equal to u times x or x is equal to u times y, which will render the differential equation separable, and you just integrate, solve for u, and of course you have the plug in the you have the relationship between u and x or u and y, and then you solve for a differential equation this way. This is the method of substitution. There are cases where the differential equation may not be homogeneous, but you could still use the method of substitution, but these relationships will not hold. You'll have to use other different substitutions in order to solve this differential equation. So let's go over an example. So here we have dy dx is equal to 2 plus the square root of y take away 2x plus 3. So if you were able to plug in lambda here for the x's and the y's, you wouldn't necessarily be able to factor it out, but you could still use the method of substitutions. Only the previous relationships that we used, meaning the y is equal to ux and x is equal to uy, won't necessarily hold. So we'll be using a different substitution such that we make this differential equation separable. So we'll be using the substitution of u is equal to y take away 2x plus 3, and then you have the derivative of u with respect to x is equal to the derivative of y with respect to x, because we don't necessarily know the function y, so we put dy dx take away 2. Now we go ahead and plug these into the original differential equations and solve. So for dy dx, we plug in du dx plus 2 is equal to 2 plus the square root of u. So of course the 2 cancels out here, and then all you have is your variable du and u and dx. So let's go ahead and separate the variable. From here you have du over square root of u is equal to dx, and from here you just integrate both sides and solve. And we have 2 times the square root of u is equal to x plus some arbitrary constant c, and we know what u is, so go ahead and plug it in. And you finally have 2 times the square root of y take away 2x plus 3 is equal to x plus your arbitrary constant. Of course, you could do your own algebraic manipulations and hopefully get y explicitly, but this is in fact your solution to the differential equations. So this video went over how to solve differential equations that were homogeneous by using a method of substitution, specifically y is equal to u times x or x is equal to u times y. But if it's not homogeneous, you're still able to use substitutions. Just use a substitution that would be convenient such that your differential equation will become separable.